Hey everybody, let's talk about gravity in better detail than we have in the past. So also assuming that the Earth is round now instead of just being flat. So the gravitational force, you just need two masses. Like here's a mass over here, mass 1. Here's another over here, mass 2. This mass will attract this mass toward it. So there's going to be some force by this one, attracting this one. And then this one will attract this one toward it like this. Right, so the gravitational force is attractive. I'll just call it F with a little g for gravity. Now, the magnitude of the force is proportional to the distance between these two masses. So I'll say some distance r from here to here. And then it looks like this. Some constant, mass 1, mass 2, divided by this distance squared. That's the magnitude. The direction is toward, right? It's attractive. Okay, and then this is the gravitational constant. Okay, and then the units. I often forget the units, but let's say you forget the units. You can do dimensional analysis to figure it out. For example, this is newtons, right? And then this is kilograms squared. This is meters squared. So just move this on this side. Move this on this side. And there you go, right? So the units for the gravitational constant have got to be Newton meter squared per kilogram squared. Okay. All right, now let's have an example of using this. Let's say there's Earth over here and like the space station. Okay. There's one force acting on the space station, and that's the force of gravity toward the Earth. Now, the one thing I have to specify, see this little point mass? It also applies, for example, to some object. And then this is just the location of the center of mass. Right, this can be some object, and this is the total mass located at the center of mass. So it's the distance between the two centers of mass. So the Earth has a center of mass, say here. So then really, and then the space station, it's the distance between these two. Okay. And then how much force is it? Like this. And it's attractive, so it's toward the center of mass of the Earth. And then the space station also attracts the Earth toward it like this. Okay, but if we just do a free body diagram of the space station, then it just looks like that with the one force by gravity. Okay, and then let's say it's moving in a circle. So let's say it's traveling in a circle at constant speed. Okay, so it's in orbit. And what does that mean? So when something is in orbit, maybe think of it like this. Imagine you're a giant standing on the Earth like this, and you throw a ball. Or let's say at first you're just standing on the ground and you throw a ball and it falls. Why does it fall? Because there's a gravitational force acting this way, right? As it's falling, there's an acceleration this way. So that's why the direction of the velocity changes, because there's an acceleration. And so the ball falls toward the ground. What if the ground is curved, like you're standing on a hill? right? Then you throw the ball, and then it falls like this. Now, let's zoom out. Now you're a giant standing on the planet like this. When you throw the ball with a velocity like this, which way is the acceleration? It's toward the center of mass of the Earth. So this way, the acceleration. And so the velocity changes direction, right? So then later the velocity changes direction. And then now the acceleration is this way toward the center of the Earth. So the velocity changes direction again. The acceleration is toward the center of the Earth. So the velocity changes again. And then like it follows and it falls. So if you throw something fast enough, it's falling toward the Earth because of gravitational attraction toward the center of mass. But then the faster you throw it, the farther it goes and it falls. So if you throw something fast enough, it's falling, and then like hits you in the back of the head. So, right, when something is in orbit, it's actually falling toward the center of the Earth, but just never hits the ground. So that's why, like, if there's the space station falling, right, it's falling, and you're in the space station also falling at the same rate, then it's like you're floating, not because there's no gravity, there is, toward the center of the Earth. It's just that both you and the space station are falling. So that's why it's like you're floating in there. Okay, just to get a sense for how far away space is, let's take a look at the International Space Station. So let's take a look right here. Okay, so the space station is at an altitude between 408 and 410 kilometers. Let's just round it up to 410 kilometers, so about 255 miles. So how far is that? So let's take a look at a map here. So we're looking for 255 miles, 410 kilometers. And you can try this yourself. So right here, this is already 200. Here, this is 410 kilometers. If you look at the reading right here, that's how far away the space station is. Here, let me maybe go from like Waianae to Hilo. No, a little bit more. There, 410 kilometers. That's how far away the space station is from the Earth. Let me zoom out for some perspective. Right there. That's space. It's that far away. When you look at it like this, not that far. Okay. Okay, so the space station is pretty close to the Earth, right? The way I draw it like this is really an exaggeration, just because if I drew it this scale, then I draw the Earth, and then I draw the Earth, and then the space station like that, which is a little dot and really close. So it's just kind of an exaggerated illustration like this. Okay, so now let's say it's moving at a constant speed. Sum all the forces acting on the space station, that mass. There's only one, g, mass of the Earth, mass of the space station over the distance between the two centers of mass squared. Okay, equals mass times acceleration. I didn't draw my free body diagram. Let's draw it like this. Let's say that's x, so x. Okay, so this acceleration is, if it's moving at a constant speed in a circle, would be centripetal. Right, so this acceleration would be centripetal, v squared over r. So how fast is this? We can solve for v right here. So this is the mass of the space station over here, right? So let's solve this for v. So we can cancel one of these r's, one of these r's. So v squared is gme over r, and then square root. So this is orbital speed. That's how fast the space station is falling. Now, what happens, like here's Earth, not to scale. Here's the space station, not to scale. What happens, right? You're falling at a constant speed. What happens if you suddenly, let's say, activate some thrusters, increasing the speed? What happens is you'll still be orbiting, but then it'll be an ellipse more so, and then the more speed you provide right here, like thrust, then you change your path to be an ellipse of different shapes. But then what happens when you go slower? When you go slower, then you start falling toward the Earth like this, and then you crash. Okay. Now, where do we get that value for the acceleration of gravity like this one? So try this as an exercise for yourself and see what you get for a number. Say this is Earth, and then let's say you're standing on the Earth. Or let's say you jump a millimeter above the surface of the Earth. So here, you're like, not to scale, right? So you jump, so you're in the air. So there's no contact force. What is your acceleration? Right, so that's called mass of the person. And here's mass of the Earth. So how far is this? That's the radius of the Earth, plus that 1 millimeter you jumped above the surface of the Earth. Okay, so what is your free body diagram? Here's you, here's the one force, my gravity, which is G, mass of the Earth, mass of the person, over r squared. How far is this? The radius of the Earth, equals mass times mass of the person times acceleration. Solve for this. If, right, it's the radius of the Earth plus that 1 millimeter, so let's neglect that. Okay, so solve for this acceleration. Give it a try. I mean, this cancels here, right? So then you basically have G, mass of the Earth, over the radius of the Earth, squared. And this is what we call G. See what you get here. So I can never remember the values, but if I just look them up again, so G was 6.67 times 10 to the minus 11. And then if you just look up the mass of the Earth is about 5.96 times 10 to the 24 kilograms. And the radius of the Earth is about 6,000, so 6.37 times 10 to the 6, 6,370 kilometers. So, okay, so try plugging these numbers in here and see what you get over here. It'll be around 9.8 meters per second squared, and that's where we get that value. Okay. So let's move on to another video and talk about gravitational potential energy. Okay, so I'll see you on that video.